Check it out now, y'all.
nanoHUB-U, online instruction.
Hi again. We're starting the fourth week of lectures in this course called Fundamentals of Atomic Force Microscopy. And in this particular lecture, we're going to talk about the cantilever mechanics. We're going to derive some of the important equations that you need to know in order to understand how the cantilever transduces a force. So there's a lot of equations in this lecture. I won't go through the equations in detail, but all the arithmetic will be provided so you can work through them on your own. I've tried to highlight the important results. So if you're just want a bottom line, those important equations are going to be highlighted in the course of the lecture. In terms of a week 4 overview, we're continuing to expand our discussion of the atomic force microscope. And this week we're going to really focus on force spectroscopy and force versus displacement curves. We're going to discuss how force versus displacement can be converted to force versus distance. And of course, once you do this, then you can start to compare your experimental measurements to these theoretical ideas that we developed in weeks 1 and 2 of the course. So we'll do a lot of discussion about how to analyze data that you obtain, not in the dynamic mode AFM, but in the case when the cantilever is static, you just push the cantilever up against a substrate. We'll try to describe the variety of different pieces of information that you can get from this really simple experiment. Today, in this lecture, we're going to really talk about the microcantilever and try to get equations that describe how this cantilever bends when a force is applied to the end of the cantilever. It's important to establish notation, and that's what this slide is all about. So here what I show is I show a cantilever of length L. I'm looking at the cantilever from a side view. I apply a force to the end of the cantilever, a point force at the end of the cantilever deflects. Right? And what I'm interested in is I'm interested in describing the shape of the cantilever deflection from its equilibrium position. So in general, the deformation or the contour that the cantilever will follow would be described by a parameter small w as a function of the distance x from the base of the cantilever, and also this displacement could vary as a function of time. So in principle, w could be a function of both position and time. For the purposes of this lecture, we're really focused on what's going on right at the tip of the cantilever. So the tip of the cantilever is located at the position x equals to L, and we define the displacement of the cantilever right at the end to be this quantity Q. So that's whenever we use the parameter Q, we're talking about the deflection right at the end of the cantilever. And then lastly, the angle that the cantilever makes with respect to the horizontal after it's been subjected to this point force F, that angle theta is a very useful number to know. And so we'll discuss how that equation is derived. So what we're interested in, of course, is we know that we assume that the cantilever has some dimensions associated with it, the width W, the thickness T, the length L. We're assuming that the cantilever is made from a material. We're assuming that you know the elastic modulus or Young's modulus E of that material. What we're trying to do is we're trying to predict W as a function of X. We're not so interested in time here. When you put time into the equation, then it's a dynamic AFM, and that'll be covered in part 2 of the course. And what we like to do at the end of the day is we like to show that we like to derive the spring constant of the cantilever K in terms of the dimension of the cantilever. We like to show that Hooke's law applies, that if you apply a force F to the end of the cantilever, the angle that the cantilever bends through is proportional to the force, and the proportionality constant is going to be somehow related to this cantilever stiffness K. And of course, if you have a useful force sensor, you like to show that the deflection of the cantilever Q is proportional to the force F that's applied. So these are things that you'd like to see come out of this discussion. So right away, I'm going to change from that notation, right? I'm going to use y of x to discuss the profile of the cantilever instead of w of x and t. Now, why do I do this? Well, the width of the cantilever is also w. That's the parameter we use to specify the width of the cantilever. In fact, we're going to specify the width of the cantilever by the parameter w subscripted by a small c. But in the derivations, I find it just much more intuitive if you instead of using w of x and t in this discussion, we use x to represent the displacement along the cantilever and y to represent the displacement of the cantilever from its equilibrium position. So what happens, of course, the mechanics of this problem is that if you apply a point force F at the end of the cantilever, you're going to generate a torque on the cantilever, and the equation for the torque is given in the first equation on this slide. Now, if you talk to mechanical engineers when they discuss this problem, they don't necessarily use the word torque to describe it. And what I found is that they use this word moment, which is given by capital M, right? So they instead of using torque or tau, they use moment M. And the reason they do this apparently is because they want to make a distinction between twisting and bending of an object, right? So when they twist an object, they tend to use the word torque to describe that. When they bend an object, they tend to use the word moment to describe it. The two quantities are essentially identical. It's just a naming convention. And so I'll try to use the word moment instead of torque to try to be consistent with my colleagues in mechanical engineering. So the magnitude of this bending moment M at a point X, when a point force F is applied to the end of the cantilever, that bending moment is just the force F times the distance x from the point where the force is applied. So since we're measuring everything with respect to the end of the cantilever, the moment arm in this case would be L minus x, as I show in this top diagram. And so, what you must realize, of course, if you've had your introductory survey course in physics, in equilibrium, there's no motion of the beam. It's just bent. It's deflected in some way, right? There must be the sum of the moments acting on any part of the beam have to sum to zero, or otherwise the beam would undergo further distortion. And so that means that there must be some internal moments generated by the atoms inside that beam that basically counteract this external moment that's applied by this force F at the end of the cantilever. So this forms the basis, this realization that the sum of the moments has to be zero. This forms the basis for describing the equilibrium shape of the beam after it's been subjected to this point force. So the way I like to understand this is I like to imagine little springs that connect the atoms inside the beam that forms this cantilever. and I try to show that schematically in this diagram. The first thing to note is there's a neutral axis of the cantilever. The neutral axis is the midpoint, and it's indicated by this red line. What I'm showing here is just a very, very infinitesimally long region of the beam, and I schematically put in springs that connect the atoms on the left half of the beam to the atoms on the right half of the beam. If the beam bends, right, the springs that connect the atoms above the neutral axis are going to extend by a small amount, right, and the springs that connect the atoms below the neutral axis are going to be compressed by a small amount. So these internal extensions and compressions of the spring are what we refer to when we talk about internal stresses that build up as the cantilever beam is met, right? So in equilibrium, torques balance torques, or moments balance moments, depending on what notation you like to use. And this means that the moment around the neutral axis is trying to restore the cantilever to its original position. The cantilever's been distorted by the application of this external force to the end of the cantilever. So these two moments, the moment from the external force and the moment from the internal forces, they have to balance in some way in order to make the cantilever shape stable. So the arithmetic behind that analysis is basically shown here. I first give a schematic diagram of the cantilever, and I show the dimensions of the cantilever in terms of TC and WC. I pick a particular point X, where X is measured from the base of the cantilever. And at any point, X, right, Hooke's law has to apply, and Hooke's law basically says the stress is proportional to the strain. The proportionality constant is, of course, Young's modulus. We discussed that back in week 2 of this course. And so you can then write down an equation that says the forces applied along any slab Y, right? These internal forces are going to be the internal forces between atoms inside the spring. That those internal forces divided by the differential area dA, indicated by that shaded slab, that shaded rectangular slab, that's got to be equal to the elongation delta L of the beam divided by the length of the beam. Proportionality constant is Young's modulus. So the area element is just the width of the beam times dy, where dy is some infinitesimally thick slab, as I've tried to indicate in this diagram. And what you have to then do is you have to look carefully in order to interpret the right-hand side of Hooke's law. You need an expression for delta L over L that characterizes the rectangular area that I've indicated. And to work that out, you have to refer to the diagram on the right side of the slide. It's basically just geometry. It just shows a cross-section of the beam. The curvature's been greatly exaggerated, but I try to show the internal forces dF. I try to indicate by the green line the elongation delta L that occurs between the atoms inside the beam. DL is going to be a function of Y, the displacement of the rectangular slab from the neutral axis. And just by going through some very simple geometry, you can show that dL over L is just equal to Y over R. And so that allows you to rewrite Hooke's law in a much more simple and transparent form. And from that, you can then start to try to calculate the shape of Y as a function of X. And the way that calculation proceeds is you have to calculate the total internal moments that are applied, and that has to balance out the external moment, F times L minus X. So you basically have to integrate this differential force dF over all possible values of Y in the beam. Since Y ranges from minus t by 2 to plus t by 2, that sets the limits of the integral. And at the end of the day, what you find out is that the applied torque has to be equal to a number of constants times 1 over the radius of curvature of the beam at the point X that you're doing this calculation. So this radius of curvature, of course, this is a quantity that showed up when we were discussing the Laplace pressure that develops at the liquid-vapor interface. The radius of curvature is a quantity that can be mathematically defined, and I just worked through the derivation of that definition of the radius radius of curvature in this slide. If you just consider an arbitrarily shaped curved line, the question is, how do you define the radius of curvature of that line? And so you need a definition. And the radius of curvature is really the change in the angle of a tangent line drawn to the line of interest divided by the change in the arc length of that line, right? So in the case of a circle, right, it's very easy to evaluate the radius of curvature, and I work through the arithmetic for the case of a circle because, right, the change in the angle of the tangent line as you move around the circle, that's just 2 pi, right? It's 2 pi radians. The change in the arc length as you move around the circle is just the circumference of the circle. That's 2 pi times the radius. And at the end of the day, you find that the radius of curvature is 1 over r. And the units are, of course, radians per meter. That we don't, when we talk about radius of curvatures, we tend not to put the radian unit in there, but really it's a radians per meter unit. If you want to generalize that discussion, then you have to use a little bit of algebra and calculus. And I work through the arithmetic of that on the right-hand portion of this slide, right? I think the calculus is pretty straightforward. It requires you to take a derivative of an arctangent function. It also requires you to take the derivative of x with respect to L, where L is the arc length of the segment defined by the line as you sweep through this differential angle element d theta. So if you just look at the arithmetic, I think everyone will be able to follow it. The final answer for the radius of curvature at a point on an arbitrary curve can be related back to derivatives of y with respect to x. And so this is a standard result that you probably derived when you took calculus in your freshman or sophomore year in college, right? So this is the standard definition for the radius of curvature of an arbitrary line at a point. It's related to the derivatives of that line at that particular point. So why do you care about this? Well, generally speaking, if the curvature is small, right, then the derivative of the line with respect to x, or the derivative of the curvature of the cantilever with respect to x, that derivative is essentially equal to 1, and that allows you to simplify the expression for the radius of curvature that I derived on the previous slide. That gives you then a differential equation that you have to integrate in order to calculate y as a function of x, right? So that's shown as the top equation on this slide. I then just go through the integration of that. That integration is pretty straightforward, and that gives me then an expression for y, how the cantilever is bent as a function of x, the distance you are from the base of the cantilever. It turns out it's an x squared minus x cubed type of shape. And if we want to evaluate the displacement of the cantilever right at the end point, x equal to L, of course, in our notation, that's designated by the parameter q. We then end up with an expression shown in the red box, which says that the displacement is in fact linearly proportional to the applied force, and there's a proportionality constant, 4 times the length of the cantilever cubed, divided by the Young's modulus E, width of the cantilever, and then the thickness of the cantilever to the 3rd power, right? And so then you can make an analogy back to Hooke's law. You can say that the force is going to be linearly proportional to the displacement of the cantilever. The proportionality constant is known as K, the spring constant, or the stiffness of the cantilever. And finally, at the end of the day, you've got an expression for K, right? And that's enclosed in this yellow box. And this is the expression that you'll find in all the textbooks and all the papers to describe the spring constant of the cantilever. On the right-hand panel of this slide, I go through and I take the results from the left panel of the slide, and I use those results to predict the deflection of the cantilever as a function of position. the deflection of the cantilever right at the end of the cantilever, right? And you can show that the deflection of the cantilever through an angle theta is directly proportional to the force that you apply. There's a proportionality constant, and that proportionality constant is basically 2/3 times the spring constant K times the length of the cantilever L. So again, this is just straightforward algebra. I think it's the sort of thing you have to sit down and work out in a quiet room on your own. But I think all the steps are here so you can appreciate what's involved. So again, I just put in a separate slide to try to clarify the notation. In part 2 of the course, the deflection of the cantilever is going to be described by this y of x and t. To simplify the derivation in this lecture, I replaced w of x and t by y of x, and in particular, the deflection of the cantilever right at the end is referred to as q, and that's the notation we'll follow for the rest of the part 1 for the course. You can take those formulas that I derived and you can make plots. So this is a plot of the shape of a cantilever. Cantilever dimensions are given. In this case, I apply a 5 nanonewton load to the end of the cantilever. The cantilever length is 200 microns. And you can see that the cantilever deflection is on the order of 400 nanometers, and it follows this shape given by the red line. You can also do linear and angular deflection plots. This is something that is useful to do just to make sure you completely understand the equations. So I guess the point is, if you want to know what the deflection of the cantilever is as a function of an applied force, you got to know what the spring constant of the cantilever is, K. So I just show the cantilever deflection versus applied force for 3 different spring constants. And then also the angular deflection. The angular deflection in microradians depends on the applied force. Again, I assume a 200 micron long cantilever, different spring constants. And you can see that depending on the applied force, the cantilever will deflect from something on the order of a microradian to maybe a few hundred microradians, depending on the parameters that you choose. There's an important implication of this that I'd just like to mention. This will come back in more detail in part 2, but this is a good point to emphasize it. You'll recall from your introductory course in physics that if you've got a mass suspended on a spring and you stretch that spring and you let the mass loose, the mass will oscillate back and forth, and it'll have a characteristic frequency associated with that oscillation that's just related to the square root of the spring constant K divided by the mass M that's been displaced. There's a proportionality factor of 1 over 2 pi in there to convert the angular frequencies into a frequency F measured in hertz. So the point I'll make is when you do this experiment, the entire mass is oscillating with the same amplitude of oscillation. It oscillates back and forth in this potential well. If you take a cantilever beam and you bend it and then let it oscillate, right? Different parts of the cantilever beam are going to oscillate with different amplitudes, right? And so that means that this standard formula that says the frequency of oscillation is going to be proportional to square root of K over M, that formula has to change. And the reason it has to change is because not all the mass of the cantilever is oscillating through the same amplitude. So it shouldn't be too surprising that if you try to calculate the resonant frequency that a cantilever will oscillate at, you need an effective mass in the denominator of this standard expression. So to calculate the resonant frequency of a cantilever beam, you have to insert an effective mass. It turns out that effective mass is about 0.24 times the mass of the cantilever, right? And when you put that effective mass in to this standard formula, then you can predict very accurately what the resonant frequency of your cantilever beam is going to be. How do you get that factor of 0.24? Well, that's another story. That story will be discussed in part 2 of the course, but basically you have to go to a dynamic model of the cantilever beam. You have to solve the Euler-Bernoulli equation. It's a differential equation. And a natural outcome of the solution of that is that you get this factor of 0.24 that can be associated with the mass of the cantilever. So stay tuned if you're taking part 2 of the course. That'll be discussed in a little bit more detail. So I've overrun my time a little bit. I think this is a lecture that you're going to have to look at some of the arithmetic in order to fully appreciate. I tried to put in all the steps, so hopefully you're not going to spend a lot of time wondering how I got from one line to the next. And I'll just say that our next topic is going to now move more into the analysis of data. We're going to start to talk about how the tip approaches the substrate and try to systematically work our way through the physics of that so that we can properly interpret that data to get information about the tip substrate interaction force, which is where all the interesting physics and chemistry lies. So we'll see you next time, and thanks for your attention during this lecture.